Okay. Well, my name is Christine Robichaud. Are we good, Chris? Okay. And I'm a doctoral student of Mark Wisner's, who's at Duke University in the Environmental Engineering Department. And he regrets that he can't make it today. He realized yesterday that his class was scheduled for the exact same time. So anyway, it's a pleasure to be here, and I'm going to do what I can to kind of fill in for him. What he decided to have me talk about is just maybe a little bit of an overview of what we do as a group, and then just do 10 minutes or so on research that I've been doing to give you a sense of what we do. So the topic is estimation of nanomaterial production for risk assessment. And what we do, as everybody here knows, risk we think of as a product of hazard and exposure. So hazard, we've been talking a lot about with the toxic endpoints, what you guys have heard already this morning. That's not exactly what we do. We focus more on the exposure portion. And so trying to talk about some of those questions that the previous two presentations had, like what's going to be the environmentally relevant concentration that you guys can use in toxicology studies, or that we can maybe point to. In our group, we also do a little bit of toxicology research just as it relates to ROS generation and some of the mechanisms for ROS toxicity on some specific bacteria and viruses. That's not my research, but that's one area, so that we do touch on the hazard portion, but mostly talk about the fate and transport that determines the exposure to nanomaterials. And what I do is not bench work on fate and transport, but more risk assessment modeling, and looking at how can we use these exposure experiments that we've done, and then link that up with the growing amount of toxicology information that's out there, in order to give some kind of semblance of a relative risk ranking, because we realize that we're going to have to talk about risk and make some regulatory choices and choices of where to put our scientific resources before we're going to know a lot of the things that we would need to, ideally. So with that said, I'll talk to you. Okay, I did the same thing. I'll talk to you about my focus. So this is a picture of, it doesn't cut off too badly. This is, we took titanium dioxide as a first pass. A lot of our work in our group is on carbonaceous nanomaterials like fullerenes, and a little bit of work with single-wall carbon nanotubes. But for this study, we wanted to look at a life cycle perspective, and really just as a proof of concept to see how far can you go to actually do even a life cycle assessment of something that's this new, and in some cases not so detectable. So we looked at titanium dioxide because it's a pretty well-established industry already in the bulk form, and it's also being commercialized pretty rapidly in the nano form. So the information that's out there already sort of dictated where we started. So this is just a basic pictorial of where we would look at, mining cradle to grave of the products, and then there are going to be these arrows kind of correspond to flows into the environment, different, chambers of the environment, and then those may or may not induce some toxic effects. So that's the whole life cycle. This is some previous work that I've done with my master's in the group, which was to sort of look at what we could do with an existing risk assessment tool that was not at all ready for nanomaterials, but just because again, we won't be able to wait for those perfect molecular models. What we did was try to look at a insurance industry risk model that they use to do their algorithms for determining their premiums for chemical companies. So we looked at the production portion of just like the materials, inputs and outputs, and some of the byproducts of making 5 nanomaterials, and tried to compare them to things that were already in the database. So we actually compared them to like wine production and some things like battery production, and without using the actual endpoint, the actual nanomaterials, we just use the inputs and byproducts to say we can look at some green engineering methods, and we can use this insurance industry framework to just get a first pass. So I was thinking of that when we were talking about the comparison, because it's just so important for it to have some context for people to read who don't do exactly what you do, but at the same time you have to pick, I guess, a context that's reasonable factually, but then also that translates to the people that are reading it. So that's how we did it for that, but we needed to move on to actually the nanomaterials themselves. So what we're doing now is looking at just these first 3 boxes, the mining and extraction, titanium dioxide production, and then what it's used for, so that we can say, just as a rough pass, how much is out there. Some of the different ways our group looks at exposure is, one, from sort of a very detailed point of view, where we say we can use all of these different fate and transport models and multi-compartment models. EPA has a really good one, and lots of people have them developed, where you can say different parameters about the environment and about the materials and where you might expect them to end up in soils and air, and that's one way to go. But then another way is to just, as a starting point, say, what if all of it got out? How big is this problem? Put some magnitude on it while we're working on telling exactly where, the molecular modeling of it. So that's kind of the focus of what we're doing with this. And then in the future, we really hope to do that specific rate modeling of how much is going to get out and with what different sources, should we be most concerned. So that's kind of the beginning. So for this portion of my research, just determining how much titanium dioxide nano may be out there in the near future. And this doesn't say anything about where, what will it all be dumped in the Mississippi River? Will it be, evenly apportioned throughout the waters? That kind of thing is obviously very important to be concerned with, but this part is just the big number. So what we need is an intercept to this line, how much is out there now, and then a slope, to tell us how fast will it grow, and how will it grow with what kind of function. No W. So okay, to do this part, we looked at USGS mineral reports, which are they're very complete for the bulk titanium dioxide. And they actually, the person who is focused on titanium dioxide says that he believes there are starting to be some nano numbers included in this, but there's no way to break it out. So for some of the cases, we'll talk about that this may already have some nano in there. But then also we looked at company data from nano producers of titanium dioxide and try to extrapolate that. So I'll talk a little bit about how we got that number and how bad it is, which is, the way that every model starts. And then we'll also look at, to try to get the slope, where we do some comparisons in a collaboration with UCLA, with Lynn Zucker and Michael Darby there, who have done some great work in forecasting and understanding the rate of biotech explosion in that technology. Basically, they were successful in sort of predicting how quickly the biotech industry would take up all of these revolutionary new technologies in the 80s and 90s. And so we looked at using some of those techniques to try to draw some parallels and see if we could get a rate of titanium dioxide growth out of that. Okay, so titanium dioxide background. I won't go too much into this, but it's interesting to look at why it's even desirable. Titanium in bulk is desirable because it has photocatalytic activity, so it can be used for just regular catalysts, or it can be used to help coatings and paints react better with the sunlight. High hydrophilicity, so we would expect it to stay in water. Lack of toxicity in the bulk format has caused it to be widely used, I think. And then it has an unparalleled high refractive index, so it makes it really white. And everything that it's used for often is because people like it to be brighter and whiter, like paper and paints. So it's used in lots of different applications, and I'll talk a little bit more about what those are. So I'm going to go through this